Shall we get you connected to the Zoom and to the
Sure, yeah,
TV?
I'm already on the Zoom.
Oh, fantastic. Nice and easy then.
Oh, thank you.
And then should we turn the laptops volume off?
Oh, yeah.
Mauricio.
Yes.
Don't worry.
Thank you.
Yeah. And then I think just chat sessions as long as attendees can chat with us and panelists. I don't know if you want to chat with everyone, but in
I'm not
general,
opposed, but so far it's been fine.
yeah, in general, just for
To be clear, that I'm sharing my screen, right?
Yes, please.
Okay. Host disabled.
Oh, okay, yes. Let me fix that. Yeah. Okay.
Okay. Let's see if I can find the right. Okay. So you said they use keynotes. Let me see if this shares correctly. Yeah, okay. Seems like no, but then this is in the way. Okay.
You can also get rid of that with, if you pull back up that meeting menu, there's an option for hide video channel too.
Yeah. Where is it?
Under
And then
more?
Thank you.
Hide video channel.
Yeah.
And you can get rid of that hide floating meeting controls on the same thing too.
So you've got some practice this. I
Oh,
Zoom all the time,
yes.
but don't ever have to put it on the big screen.
Alright.
go ahead and get us started with your introduction then. It's 5:30. All right. So, hello everyone. Thanks so much for coming to Popping the Science Bubble. We're going to go ahead with our land acknowledgement, introduce our Science Bubble team, and then we can get the program started. So, Berkeley Public Library buildings are built on the territory of the Huchun Chochenyo-speaking Ohlone people. We honor the 5,000 year history of the communities of the West Berkeley Shaolin and the current Ohlone communities in the city of Berkeley and throughout the Alameda County and the East Bay. The library recognizes that Berkeley residents have and continue to benefit from the use and occupation of unceded stolen land that makes the namesake of our city, and our city has benefited from and advocated for settler colonialism and the forceful conversion of indigenous children to Christianity. Berkeley Public Library is committed to helping create a more just and anti-racist society and furthering the visibility and celebration of Ohlone authors and culture in our collections programming. All right, so welcome to Popping the Science Bubble. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic that they just find really interesting. The organizers are 3 graduate students at UC Berkeley, Taylin Zong, Daniel Bretthauer, and Madison Lemer. Lectures happen on the 3rd Tuesday of the month at 5:30 p.m. These programs are live streamed on the Science Bubble YouTube page, so you can view them later and share them with others. Popping the Science Bubble also has a website and a listserv that you can join to keep up to date on new Science Bubble lecture topics. All right, thanks so much, and I'll let Daniel introduce our first speaker.
Thank you so much again for being here. So, as Kelsey mentioned, we host our talk 3rd Tuesday of every single month, and we'll have a QR code that you can use to sign up to the listserv if you ever want to hear more, get more of our emails and whatnot. So for tonight, we are very excited to have Raymond and Mauricio. And so this is an open format talk. So please, if you have any questions throughout, raise your hand. Don't be afraid to ask any questions. I'm sure our speaker will be more than happy to discuss things. And for those of you who are in our Zoom audience, you can go ahead and put your questions in the chat there. So to start us off tonight, we have Raymond Ehlers, and Raymond is an experimental physicist investigating the properties of the strong force via collisions of nuclei accelerated to nearly the speed of light. Growing up in Oregon, he received his BA from Columbia University and his PhD from Yale. After obtaining his degree, he was posted in Geneva, Switzerland for 3 years, working on a Large Ion Collider experiment, or ALICE, at the Large Hadron Collider, LHC, at CERN. During that period, he was a postdoctoral scholar, first with Oak Ridge National Laboratory, and then transitioned to a position with UC Berkeley and Lawrence Berkeley National Laboratory in late 2021. He reallocated to Berkeley in early 2023, where he is currently a postdoctoral scholar as a member of the Relativistic Nuclear Collisions Group in his Nuclear Science Division at LBNL/UCB. Raymond, please take it away.
Thank you. So we have a nice small group here, so really please feel free to interrupt as I go through this. I will, kind of cover everything that we need to know, but I also include some other details if you know a little bit of physics. So, if it's there, please feel free to ask about it. So my goal here, as quick as we can, is to get to really the heart of all the matter that surrounds us, getting to really the basis of kind of what everything is made up of. And so to get there, I want to just highlight a brief, simple scientific principle that I think everyone's going to be familiar with, but will give you, I think, really a concept that even now, these years later, we still apply and take advantage of. So we're going to start very simple, thinking about, what are objects made of, right? And so you can start, there's a couple simple ways you can answer this. One is the most simple way. You can just look it up, right? I've given you some table, it's wood, we're done, right? We can go to questions. Or we can try and do a little bit better, think a little bit more scientifically. We can think about trying to investigate the properties. So trying to figure out, how do we actually know what something is, right? You can look at it with your eyes, you can try and push it around, you can see how hard it is to move, for example. You can try and lift it up, you can see if it's heavy or light, or how the weight is distributed, right? You can try all these different approaches, if I'm just starting right away, right? I can always, for example, try and do this a little bit more systematically. Say, I pick up a dumbbell and I drop it in various places and I see how strong the table is. Maybe I break through it at some point, which tells me, again, something about the materials that I'm trying to investigate. Or if, I'm feeling very sophisticated and I want to do something very systematically, maybe I have some scientific tools, maybe I shoot a laser at the table, try and determine its composition, right? You can all do all kinds of things, right? Different levels of what you want to do, right? But fundamentally, the point is, right, I want to have some calibrated method, right? And I want to just try and investigate each, property of whatever I'm trying to look at in a systematic way. And based on that, I can start to kind of build up my observations and actually come up with some hypothesis on what it is and how do I understand it, right? So that's kind of the general principle I want you to keep in mind as we go through this. Now, I want to talk about really, how do we understand matter in its most fundamental way? And so if we're going to do that, we need to go small, right? We need to look at the details. And something you want to keep in mind is, as we do this, right, if we're going to go small, it helps us avoid things like complication, right? If I'm looking at a wood table, maybe there's moisture in the air, that's going to change its properties, something like this, right? So I want to look at something small. I want to look at a pure sample, right? If something's contaminated, it's going to be hard to figure out whether it's from a contaminant or from my, material I'm interested in. And I want to be able to isolate it from everything else, all these environmental effects, all of this. Right, and so I want to think about the scales that we're going to talk about, right? So if I start with my table at some meter size, right, we're going to start zooming in by factors of 1,000, right? So if I zoom in here, if I get a microscope, for example, I can look at the surface of the table, and maybe I see a very large single-celled organism on the order of a millimeter, right? So it's 10 to the minus 3 meters, right? And I can keep playing this game, looking closer and closer and closer. Maybe I get a nicer microscope. Maybe I shine some more light at it. I can get a better view. Right, and I can start to go and see for example, the structure of my wood, right? This is about a scale of a micrometer, right? So we're going down another factor of 1,000. I can keep going at this game, right? I can go from my wood cells, and then I can start to see, for example, the atoms, what they're made up of, right? And I'm starting to really kind of get into the components of the matter. And now we've gone down another factor of 1,000. We're down to now the nanometer scale. So I can continue to play this game. I'm going to keep going even further and further. I want to look inside my atom. And I hope everyone's familiar. We know that there's a nucleus in the middle. This nucleus is made up of these semi-fundamental particles known as protons and neutrons. And so we've gotten to this point. So now we haven't quite gone, or now we've gone down a factor of 1 million, in fact, down to 10 to the minus 15 meters, unimaginably small. So what I want to think about here, though, is right? We've gotten to this tiny, tiny scale. How did we actually figure out where we've gone, right? I'm far beyond this point where I can just use a microscope, even a very fancy one, to kind of look into the details of this. So how am I actually able to do this? So the way we're going to do this is what's colloquially known, at least in the physics community, let's say, as a Rutherford scattering experiment. And it's a really simple concept. All I'm going to do is I'm going to take some sort of, again, my calibrated probe, in this case, some beam of particles, and I'm going to shoot it at an isolated sample. In this case, it's going to be some gold foil. It's very thin. And I know a little bit about my atoms. They're mostly empty space. And so what happens is when I shoot my particles through this, most of my particles, let's see if this works. Yeah, it's hard to see on this, but okay, fine. In any case, most of my particles are just going to go straight through. There's nothing to interact with. They just go right through. However, every once in a while, you're going to see a particle reflect almost back at you. So collide against some hard object and come back. And this is basically proportionality. It's like if I shot a cannonball off a ship into thin air and it bounces back at me. It's a very kind of striking concept, right? And this tells me that there must be something, some structure inside of there that I can try and detect. If I do some analysis, then I can try and figure out what that structure actually is. So again, it's this concept. I'm trying to poke and prod whatever I'm interested in a way that I understand, to then try and be able to understand what is actually in this surface of, or this object of interest. So this is where we have to get a little bit more schematic, but we can in fact keep playing this game that we've just done all these scales down, and we can start to try and look inside of what's inside of these protons and neutrons here. So again, protons and neutrons are inside our nucleus. We're going to look even shorter, even further inside. So to do that, I need to go to shorter. I need to have something that goes to shorter distances that I can see further in, and to do that, I need to go to higher and higher energies. So the details don't matter necessarily so much, but the concept is exactly the same. And if we do this, what we get to is we in fact see some additional structure inside of our protons and neutrons. And now we've really gotten to, as far as we know, the fundamental point. So we have these two types of particles, quarks, which are these circles here inside of our protons and neutrons, and gluons, which are these coils, which conveniently enough kind of glue they tell us how these quarks interact with each other. They kind of glue them together. And we're now on, again, this unimaginably small scale, right? So I have to just keep trying to put in these high energy particles and see if I can make sense of it. So if I go back to my principles that we started with, right, I want to get a small isolated sample of this, right? I can kind of get something in my proton, but it's not isolated. There's different impacts inside of it, right? So I want to try and get one of these quarks, pull it off, and look at it in my lab somehow. What happens when I try and do this? Well, usually you'll start with a pair of quarks, okay? And I'm going to start trying to pull them apart. I'm putting in energy, I'm putting in work, and I'm pulling them further and further apart. And as I put in further and further, as I pull them more and more apart, I put in more and more energy. And in doing so, I put in so much energy that I create a new pair of quarks out of this energy, out of nothing, right? Out of the vacuum. It just shows up out of this energy. And this is, kind of a fundamental result of, from Einstein equals mc squared, which at least I imagine some of you have heard of. We can talk about this more later, but basically it means no matter how much work that I put in, I can never get an isolated sample of quarks. Really, really kind of a problem if I want to try and study it. Okay, but we have a way out, and this is where we get to our smashing part. So what I'm going to do is I'm going to take a nuclei, but now a really heavy nuclei, lead. I'm going to smash them together at very high energies, and in fact, very, very, very nearly the speed of light. So close, it's almost a rounding error. And in fact, they're going so fast that because of relativity, again, the same thing from Einstein, these spheres now get flattened to pancakes. They're basically, like sheets of paper. And I'm going to have them collide together. And when they collide like this, there's going to be so many collisions between all the particles where they're carrying all of this energy that it then puts it into one place. And I get a new state of matter called the quark-gluon plasma. It's this whole orange thing here. And what the key is that my quarks are finally almost like they're free. Not quite, but it's very close. And so I can use this as a tool to finally get back to study my original principle, right? I want to have this original free quark and trying to be able to study it with some probe. Now, a few things about the quark-gluon plasma. First of all, the name is entirely counterintuitive. It's not a plasma at all. We named it long before we knew what it was. What it turns out is you can think of it kind of like in the same concept as if I transform my ice into water, right? I'm just changing the phase of it, but I'm doing it for this type of matter that lives all around us, governed by this one of the fundamental forces, this strong nuclear force. So what's odd about it is it behaves as what's called a perfect fluid, which means basically that it's, I'm trying to find my mouse here, we can play a simulation, but there we go, all right. So we see the two nuclei collide, basically going through what this animation just showed you. They collide together, we have these interactions, we form this plasma in the middle, and then all these balls coming out are all different particles that were produced that we're going to find in our detector and try and kind of reconstruct as if you're a crime scene investigator, almost trying to figure out what actually happened in these collisions. And in this quark gluon plasma phase, everything interacts to each other kind of perfectly. In doing so, we've kind of recreated conditions of the early universe, a microsecond after the Big Bang, and it's really a thing of extremes. It's 5.5 trillion degrees, so a million times hotter than the sun. It is all kinds of, basically, pick your superlative, it applies here. So how do we actually do all this, right? I've said we're going to, but how do we do it? Well, we do it using what's called the Large Hadron Collider in Geneva, Switzerland, which we have a nice animation here, like, oops. Okay, well, let's see if I can get this to behave. What happens is basically these particles are accelerated in a series of rings. They're going to get faster and faster and closer to the speed of light. We have 4 different collision sites where they happen, and now it's going to zoom in on the beams as it's coming in. And we can see in this visualization, these particles are going to go through what this is in blue is our beam pipe here. They're circulating around 11,000 times a second underground, about 100 meters on the French-Swiss border. And they're going to go into these 4 detectors we have, which serve as basically giant digital cameras, giant 3-dimensional digital cameras, in fact. And we will see that they collide together here. And in doing so, they create a whole mess of particles. All of these lines that you see coming out are all tracks that we can then try and detect in our collision and make sense of. Now this happens millions of times per second. We collect unimaginably large amounts of data, and we then have to go back and try and figure out what actually happened in all these cases. So I will, for the sake of time, I think I'm running a little long here. I'll skip over the video of my particular experiment. It's called a Large Ion Collider experiment. We're very creative, but we call it Ehlers. And so it is this absolutely massive detector here. This is 6 stories tall. It weighs 10,000 metric tons, the same as the Eiffel Tower. Mm-hmm. It's 100 meters underground. It's absolutely massive. So
you're fine on time, by the way.
Okay.
So don't. Yeah.
Okay. Well, then let me play a little bit of this video then. So we can see, if we zoom in here, we're zooming into Geneva from the globe. If you squint very carefully as we zoom in here, you might be able to see my old apartment. So we have the lake here, and it's going to show you have the whole ring here in Geneva. This is all underground. You can't see any of it. And in fact, when you go, for example, to Ehlers, you're really just walking through this beautiful French village, and suddenly you turn the corner and you have an industrial site. So that image there is a full-size scale of the detector. We're going to see just a little bit here going into the control room, where we have 4 people running the experiment 24 hours a day, pretty much the entire year. Spent many long nights there. It's mostly boring until chaos happens, but when something is broken, but it's a nice experience. So you can see we do all this, we're running it all together. It's really a collaborative effort with collaborators from 40 countries, about 2,000 people. So it's really an absolutely giant effort. So we're going down now into the tunnel, and you can see the experiment here. So you get these nice views. The beam is coming in from both directions, so now coming out from the screen. They collide in the center there, and all of these are all different detectors that we've developed, 23 in total, to try and make sense of all of these collisions. So one more view of it, just to give you a sense of scale. And really the thing that I want to highlight here, I mean, there's lots of complexity, we can talk about it, but these are the people for scale, or alternatively for scale, me standing on the other side. Again, it's absolutely huge, right? We've built this absolutely giant detector to find the smallest things we can come up with. So we're almost there, but what I want to really kind of make sure we understand is that in one of these collisions, right? We have each of these lines represents a particle with different colors kind of representing different species that we can identify. So this is from one collision, we get thousands of particles. So we really have to be very careful and very judicious in determining what actually happened, right? Because I don't actually see those lines. I just see basically dots on a computer that I have to figure out the right way to connect using my knowledge of whatever data we have, whatever detectors we have, and whatever physics we have available to us. So it's really, Ehlers is now almost 30 years old. It's been a long effort to get to this point. So we have all this set up. I want to loop back to where we very much started, back at how do we figure out how matter works, right? So I've got one more cartoon here of my collisions. They've just interacted, and we formed our quark gluon plasma in the middle here. So, right, I want to have some calibrated probe. My first thought, or at least when I was an undergraduate student, was, all right, let's find a way to shoot a laser through it. That would be great. The problem is that this collision happens so quickly that in the time of kind of our shortest laser pulse, 1 million of these collisions would happen. So, lasers out, right? But we got a little bit lucky. It turns out that in rare cases, when these nuclei collide, they will collide at one of these quarks, for example, in one of the protons and neutrons in this, right, will collide with very high momentum. What this means, it will happen very fast, and it will actually give us a calibrated probe, self-generated by our collision. So it's a little bit messy. We have to be able to figure out what happened, but it actually turns out that it gives us a probe kind of built in that we can then try and use to actually figure out what's going on. So we're using quarks to figure out what happens with other quarks, basically. So my last bit here then is to, the reason why I talked about this Rutherford scattering experiment was not just by coincidence, but in fact, we're trying to use the same concept developed more than 100 years ago, but now in a much more sophisticated way instead of in our quark gluon plasma. The idea is we want to find one of these self-generated quarks, and we want to try and look for its interactions with the quark gluon plasma, because it turns out that in most cases, when this quark goes through it, it interacts very, very coarsely, but it doesn't see any of the details of the plasma. But very rarely, we have good reasons to expect that the plasma will kind of excite. It will have some sort of special interaction, let's say, and in doing so, we might have a chance to actually have our quark scatter off of this. So our goal is to try and do this, and if we do, it really will tell us something fundamental about how matter actually fits together. So in the spirit of trying to share a little bit of science, I wanted to very briefly show what this actually means from day to day. I will explain, you don't have to understand what this is, I will explain exactly what it is, but I want to just highlight, with a little bit of explanation, these things can all kind of be made sense of. So we have two methods to try and do this thing that I just talked about, trying to use scattering to make sense of it. One is when I do a deflection of a jet. So if I have my quark that I found kind of go in both directions, I have a pair of them, and I just look at the angle. That's all I have to measure, and try and make sense of that. And my second method is instead of looking at kind of both sides, both the particles coming out, I look inside at the details of quark, trying to scatter off this quark gluon plasma. That's all I have to do. So conceptually, it's very simple. And these results came out of, results that myself and collaborators have been doing in the last couple of years, all recently coming together now. And the concept here is, all you need to know is that I'm going to tell you, both these plots are showing basically some modifications. So what happens when I have the plasma versus when I don't. And the expectation, if I saw that structure that I said we're looking for, is everything's going to sit all together. But we see, in fact, that if I look at my data points here, the dots in the different colors, there's this huge gap. And so this is quite unexpected. It tells us that there's some additional details of all the structure that we don't understand yet, or at least we have some understanding of, but maybe we need some additional handles to be able to kind of make sense of the details. Same kind of story over here, but in a different way. Just saying that on that far right side, our expectation is that we'd see some excess if we saw this structure, but that's not what we see instead, which is again kind of telling us that in this case, we're overwhelmed by kind of other effects. So all I really want you to come away from this is that we have some kind of basic understanding of what's going on, but we have some basic properties, but still, science is very much an iterative process, and we're trying to make sense of the details of all of this. So to briefly summarize, right, all I really want to say here is that science can be very complicated, but the concepts we need can be quite simple. And there's a lot of power, in fact, in that. I told you a little bit here about this so-called quark-gluon plasma and a few different ways we've tried to study it.
Wait, can I ask a
Please.
question? Is what's going on with, so you said something about like the quarks are the probes, like what is, where are you getting these quarks?
Yeah.
What is, so you're trying to, you have the thing of quark-gluon plasma that you got trying to glue everything together.
Right.
And then what is their, collision generates their own probe? What does that mean?
So what I mean is that when one of these nuclei collide together, right, I have, a ton of protons and neutrons, and inside of those I have a ton more quarks and gluons. And so when I have them collide, it's not just that one of those collides together, but thousands do all at once. And so when I say that we form this quark-gluon plasma, these are mostly with kind of very low energy collisions. They're just glancing, but they kind of share a little bit of their energy. But then when I talk about these self-generated ones, what I'm saying is that in rare cases, one of those hits really hard. And so that when it hits really hard, it will happen much faster, which means it gives us the opportunity to actually kind of pick it out afterwards. And so, where is it coming from? Everything is coming from the same collision. It's just kind of, they interact in different ways, and that gives us the chance to see them differently. Does that make sense? I think that was my point here. There's some nice physics here. I hope this expanded your interest a little bit, and I'm happy to answer any questions you might have. Thanks.
You said there's 23 different kinds of detectors inside.
Yes.
Could you explain how maybe one of those works?
Absolutely.
You described it like a digital camera, which I sort of understand, but how do you detect quarks flying?
Yeah, so that's an excellent question. So to first just answer it kind of broadly, the reason why we have so many different kind of subdetectors is because there is no best way to see particles. They all kind of interact a little bit differently. And so for one example, I should have included this, but this large cylinder here in blue, it's called a time projection chamber. So what we do is we have a bunch of gas in this cylinder, and as particles go through that cylinder, particles are produced, it will ionize those gas particles, which leaves kind of a signal. You can imagine it, I really should have brought something to draw on, but okay, you can imagine, you get some, along the path of the track, you see basically all of these different ionization points. We put a magnetic field on this, and it floats it down towards basically the two ends, and we can read out what happens, basically the time information when those arrive, which then gives us really a 3D picture, very much like this. So all of these tracks in green are all from the time projection chamber, and we've done things to kind of clean them up and make sense of them, but approximately that's really kind of what you see. There are many different ways to do things. You can use really just silicon chips. I mean, with the same manufacturing process to, let's say your phone. We also take advantage of those. There are benefits and trade-offs. So that's kind of the general prospect. I will make one last comment, if you'll indulge me, which is to say, so for the same reason that we can't get our quarks, a free quark on its own, this also in fact means that we can't directly observe quarks. So what actually happens is when a quark ends up kind of on its own, so if I have a quark coming out of my plasma, for example, right, if I have, for example, this red one kind of coming out, once it ends up outside of this medium, it will basically create a shower of particles. So it'll create many more lower energy ones, and those are actually what we can detect. So those are what are called hadrons, but what it really just means is that they don't have kind of these quark-like properties. And so we have to figure out, it's just another step that we have to then figure out how to actually make sense of it.
Fascinating talk. So from the examples that you gave today, that's with lead particles. Is there a reason that we're using lead, and can you use two kinds of material?
Yes, absolutely. All very good questions. So, why are we using lead to start with? So, what you want generally, so there are kind of various things you can optimize, but generally, right, I want to put a lot of energy in a small place. And so the heavier nuclei I have, the more energy I can put in that small place. Lead is particularly convenient, both because it's what we have accelerator capabilities for. I mean, so some of it's pragmatic, but also it's lead turns out to be what's called doubly magic, which is a great name, which I probably wouldn't explain right now, but it means basically it roughly means it's very, very spherical. It's very uniform. And so this can be kind of convenient for trying to understand this. That being said, though, this is definitely not the only way to go. So, for example, there is a similar accelerator in New York called the Relativistic Heavy Ion Collider, and they use gold instead. And why gold versus lead? Again, just kind of what was, these facilities have been around, kind of the precursor facilities have been around for 40, 50 years. So if you have a capability, you want to maintain that capability, and the differences are, important and have to be accounted for, but can kind of be manageable. And then you also ask, can you collide different things? Often, yes. So it depends. Again, it kind of depends on what facilities or what capabilities are available. One thing that's commonly done is to collide, for example, a proton with a whole nuclei. And so in doing that, you again kind of get your same concept of calibrated probe colliding into bigger material. Complications to this, but generally, so you can kind of use this as another handle to try and figure out what's going on here. There's lots of interesting things you can do with that if you have the time and the resources. But, yes, please.
I'm kind of curious. You've been talking about we use the quarks themselves as a probe.
Yeah.
Do we see imprints of the gluons in this quark gluon plasma, or how do we know that that's there?
Another excellent question. So yes, we do see gluons. So or we see gluons in the same way we see quarks. So we're never going to see them free on their own, but we are going to kind of be able to detect them and in a very similar manner, let's say. And so actually being able to disentangle, if I look kind of at each individual event, whether some set of particles came from a quark or a gluon is actually a very deep theoretical question that's very tricky. All that is to say, we have very clear evidence it's there, and I mean it kind of has to be based on. So to add just a little bit of terminology, all of this strong nuclear force is governed by what's called quantum chromodynamics, which is just a fancy name for basically describing kind of how these particles interact in kind of a theoretical way. And these gluons are very, very weird, right? A gluon carries the force in the same way that like a photon carries electricity and magnetism, which is to say kind of it signals to you that that force is there. But what's very weird about gluons, or if a photon acted like a gluon, if I instead look at a light, all I would see basically is a amorphous blob all around me that's just bright because they interact together in a very complicated way. So that's what is my point of this is that this is something that we kind of actively study, and we really want to try and differentiate these things. There are some kind of theoretical reasons you can, but also it turns out that interacting in the medium mixes them mixes their signals together. So whatever would differentiate them becomes that much harder to figure out. Does that answer your question? Okay.
And let's thank Raymond.
Great, thank you, Raymond. That was very interesting. And now I'm going to introduce our second speaker for the night, Mauricio Lopez. He was born in Mexico and received his bachelor's in chemical engineering at the National Autonomous University of Mexico. He did his PhD in Berlin, Germany at the Max Planck Society Fritz Haber Institute. Currently, Mauricio is a postdoc at the Berkeley National Lab, but at the Advanced Light Source and Chemical Sciences Division. He enjoys climbing and hiking and dreams of making a contribution to wildlife conservation in his lifetime. Take it away, Mauricio.
Thanks a lot. Very kind introduction. So I'm basically here to talk about a bit the science that is done in the Berkeley lab here. So I think everybody have seen this dome-like building.
Mauricio?
Yes.
On Zoom, you are sharing your presenter view, just an FYI.
So we can see.
On Zoom, but I mean, we can still see a slide if that's not a
I wonder
problem.
if that's maximized.
But we see your notes too.
They have no notes.
I mean, we can still see your slide, so it's not that big of a deal, but I think, yeah, sharing the,
Do you know how
Screen
can I
instead
make
of-
it the full screen?
when you share your screen, choosing screen instead of an app usually allows you to do that.
I'm gonna try.
Into or desktop to.
Thank you.
I'm sorry for that.
No?
No worries.
Anyway, I wanted to show how it looks like from the other side. So this is the, I mean, first of all, I would like to share what a synchrotron is, why it's on the here, it's on the title, and some quick applications about the design that is done over that. And this is the typical view from the synchrotron. So it's known as the Advanced Light Source, or ALS. It's basically the core building of the Berkeley lab on the hill. And what is very historical is what is just in this square, in this section. And then if you look inside of it, this is basically a cross-section, a render of how the Advanced Light Source looks like. There is like two main components on it. Something called booster ring and a storage ring. It's actually very interesting that was just mentioned the Hadron Collider, because this is basically the same concept of technology, but smaller. And the key difference is here, instead of accelerating nuclei to crash one against other, you're accelerating electrons, but then we can play with them and create X-ray source from them. That's like the main tool of this device. In more human-friendly concept, this basically is a fancy microscope that can see more than just images. We can see a spectra. That is a bit more tricky concept, but it's just information about the matter. It helps to study the matter. So I think the easiest way to understand how a synchrotron works is basically by the main components of it. I taught 9 essential components on a synchrotron. They are just basically the name of all of them. But I think it's going to be easier if we make like a kind of analogy with all of them. So everything in a synchrotron starts at the number 1, that is the electron gun or electron source. And this is not different from a bulb. Like these old-fashioned bulbs that I think now they are very popular at the IKEA. That is like a material, in this case tungsten, that you apply a voltage, a very high power, electrical power. And then it's so high that it starts shooting electrons. Then these electrons are collected and accelerated further in a linear accelerator that is basically like a long tube. Everything is in vacuum. And you can see this linear accelerator like a wave. So think of the electrons, they start like surfing on waves, just like a surfer does on the sea. And then when they are on the top of the wave, they gain some energy and start going faster, 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 and faster. And it's intended that these electrons should be as fast as possible, close to the speed of light. So then there is something called the booster ring, that is basically this inner ring. And because the linear accelerator in the ALS is very small, you cannot accelerate it too much. So then you put it like in loop, and then you keep applying power, like small waves, to get faster, 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 and faster. Then we have the storage ring, that is like the external big ring, that in essential is